and a sine 3x. And these are coming from, both of these are from an e to the 3ix. So this is how the story goes. If we have a repeated linear factor, we get exponentials or x times exponentials. If we have an irreducible quadratic factor, something that requires complex zeros, then that gives you sines and cosines and products of sines and cosines and exponentials. So this one, the general solution, c1 e to the 3x, c2 e to the minus 3x plus c3 cosine 3x plus c4 sine of 3x. That's the general solution. Look at another example. At some point, it gets annoying to try to present your examples like that. So it's more fun to write them like this. D squared plus 4d plus 5. D cubed. Y equal to 0. We can look for the solution to this guy. Okay, admittedly, I could figure this out. This would be like the fifth derivative of y plus 4d to the y to the fourth derivative plus 5y prime 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 equal to 0. But, you know, this is better. All right, so this, all right, is d plus 2 quantity squared plus 1, all right? And just to show you, that's d plus 2 minus I, d plus 2 plus I. So generically speaking, if you complete the square and you're left with something squared plus something, it's irreducible, and it factors like this. Like, here's a general algebra comment. I need to put it somewhere. I'll put it up here. If I have x minus alpha quantity squared plus beta squared, that's equal to, I guess I need to find x minus alpha plus I beta times x minus alpha minus I beta. Anytime you complete the square and you have a sum of squares, that means that you got yourself an irreducible quadratic factor. Here's a little fun algebra fact for you. So putting that into practice here, I got that. So I can look at whichever one you like. I'll look at this one. This tells me that my lambda is minus 2 plus I, right? This one, lambda equals to 0 thrice, right? Any in theology? No, otherwise, the likelihood somebody said thrice today is somewhat low. Let's see here. Okay, so this gives me e to the minus 2x, minus 2 plus I times x, right? As a solution, a complex solution. This gives me y equals to what? E to the 0x, x e to the 0x, x squared e to the 0x as solutions. But so the complex one, that's e to the minus 2x cosine x plus I e to the minus 2x sine x. And over here, of course, you can clean this up. That's 1x and x squared. So there you go. You can see your 5 fundamental solutions as they're known. And from these, I can construct the general solution. The general solution has the form y equals to c1 e to the minus 2x cosine x plus c2 e to the minus 2x sine x plus c3 plus c4x plus c5 x squared. That's the general solution to that differential equation. Every single possible way you can solve it is contained in that formula. We did. Oh, it doesn't matter. That's the beautiful thing, is that would give you the same thing but with a minus. Okay. So the cool thing is whenever we have a conjugate pair, one of each members of the conjugate pair gives us everything we need.
Okay.
Yeah.
You showed that before earlier, right?
Yeah, but that always bears repeating. That's a good question. Anybody paying attention should ask that question at some point. At this point, by the way, we can go back. I mean, there's a lot of questions you could ask about my lecture today. Why? Why do that? Well, I just think it's important for you to see the big picture, and the only way I can get the big picture to you is to show you everything at once, and that's what I did. Now you know how to solve, if you follow me, arbitrary constant coefficient problems, homogeneous problems. I mean, what's the rub? If I write down y, the fifth derivative, right, plus 4y prime 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 plus 3y prime 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 plus 2y prime prime plus 3y prime minus y equals to 0, I can't solve this. Why? It's pretty simple. It's because I don't know how to factor lambda to the fifth plus, or I'll write it in x so it's more friendly. Do you know how to factor a fifth order polynomial with ugly coefficients? Can you factor that? I personally cannot do this. Right. A lot of modern algebra has been constructed, invented, was given birth to, and essentially to show that finding a formula like the quadratic formula to make that happen is impossible. This is a quintic. You can't factor it by close. There's no quadratic formula for something like this, generally speaking. So that's always a stumbling block for us, factoring, right? Which is why many of the problems I give you are nice, right? Like that one I had erased here, the fourth power. That's a difference of squares, right? So that's not so bad. One more example, we'll call it a day. Suppose I have d squared plus 60 plus 13, square that thing, y equals to 0. This is a fourth order differential equation. I guess I could find it explicitly for you in y prime prime notation, but it's kind of beside the point. How do you find the solution? Well, complete the square. So that's d plus 3 squared, right? So that adds 9. I got 13 here already, so that means I say plus 4. But that is equal to d plus 3 minus 2i times d plus 3 plus 2i. Both of these squared. So this gives me then, right, like y equals to e to the 3 plus 2i rather. I'm an idiot. Minus, you got to remember, this is where you guys make a mistake a lot of times. Remember what we're looking at in here, we have to think about d minus lambda, right? So I have to write minus 3 plus 2i times x. It doesn't matter whether you use, I just like to make the imaginary part positive just for the sake of one less minus to fuss with, you know? It's up to you. But that's a solution, complex solution. And this is also a complex solution by the lemmas we developed today and by the homework you did. And from that, we get a sine and a cosine, and sine and a cosine times an exponential. Like this is e to the minus 3x cosine 2x plus I e to the minus 3x sine 2x. And then the other one, of course, is the same thing but with x in front. And so, my general solution, y equals c1 e to the minus 3x cosine 2x plus c2 e to the minus 3x, all right, sine 2x, plus c3 x e to the minus 3x cosine 2x, plus c4 x e to the minus 3x sine 2x. There you go. That is the general solution to this fourth order problem. So after you do about 10 of these, it should really sink in for you. I mean, I know it because I've derived it, and, you know, it's in my blood. But it's really not complicated what I'm saying. What I'm really telling you is something shocking. Solving the nth order constant coefficient problem is just a problem of polynomial factoring. It's a problem of polynomial algebra. We don't have to integrate. We don't even have to differentiate after we build the machine. It's just algebra. That's it. So next time I'll talk to you guys about what I mean by independence and a little bit more on the theory of the problem and applications and so forth. Let me give you your book because I don't want to carry it all the way over here again.